Hey everybody. Thanks for the introduction. My name's Joe from University of Wisconsin-Madison. I'm going to be talking a bit about some classification models that we've developed for trying to give some more real-time and forecasted information about solar curtailment in the California grid. So we could probably have an entire conference dedicated to solar curtailment in the California grid, or CAISO. But the big picture is that it's happening on a huge scale with dramatic growth year over year, which you can see here. So far in 2024, at least as of May 1st, I think there's maybe some May data out there now, but we're at about 1,900 gigawatt hours of renewable curtailment. And 840 gigawatt hours of that has come in April alone. So to put that into context, that's about 31 hours at the peak load from a few days ago. So we're talking about pretty large amounts of energy here. And for this project, we focused on solar curtailment because it outweighs wind in magnitude by about a factor of 10 to 1. So our motivation for trying to give more access to curtailment data is basically just that it might be useful for informing emissions reduction or load shifting schemes. This is actually just a chart of some statistical information for how curtailment varies in different months and hours. But you could imagine if somebody gave you at the beginning of the day something like this rectangle and told you when there was going to be curtailment, you might be able to change your behavior, like when you charge your EV or something, in order to try to use some of that energy that would otherwise go to waste. You could also imagine combining it with some kind of marginal metric like locational marginal emissions in order to give some sense of headroom or stability to that metric. Yeah, so the issue here is that while curtailment data might be nice to have, it's currently not made available by CAISO in real time, and it's certainly not forecasted. It's about a month delay for nice 5-minute data that's not buried in a PDF. So our goal with this project has been to try to see if we can map from some of these grid metrics, which are available in real time, onto some kind of information about what's going on with solar curtailment right now or on a 24-hour horizon. Yeah, so in order to do this, we developed 2 different classification models. From a machine learning perspective, very, very simple stuff here. These are just binary classifiers implemented with XGBoost. But the 2 kind of key qualities of both of them is that they're both real-time deployable. So any information used as an input feature is publicly available via API in real time. And secondly, they are tuned to be maximally useful for load shifting applications, which we have interpreted to mean that they are precise. So we're trying to not have shifting costs, whatever they may be, incurred based on kind of erroneous shifting when there is no curtailment actually in a given time step. And secondly, that we have high sample recall on large curtailments, which I'll talk about more in a second. But essentially, just we're concerned with identifying the most significant shifting opportunities. So to head off a couple of questions that will probably come up, we're doing classification instead of regression, basically just because regression seems to be quite difficult using this data. And it seems other people in the literature have run into the same thing. These folks tried doing regression using similar data from CAISO with a huge range of regression models, and their results were not very compelling for regression anyway. So we've just gone with binary classification. And XGBoost, that's a pretty easy one to justify, but great track record for tabular data, as well as in our tests seem to be better than lightweight linear models, but no worse than more complex neural network-based models. So for our data sets, everything comes from CAISO for this. All of the input features come from CAISO's real-time information system, which is called OASIS, and they're all available in real time via their API. And then historical data for our, the labels here, the curtailment data, also obtained from CAISO, but of course not available in real time, or we wouldn't have done this project. And specific input features, these differ between the real-time and forecasting classifier, obviously. For real-time, we've got a handful of supply features as well as real-time demand and net demand. And just for clarification, when I'm saying net demand, that's just demand minus renewables. So that's renewables is this gap here between demand and net demand. And then we also have a few time-based features as well. And then the time frame that we're working with here, it's about 3 3/4 years worth of data. The forecasting classifier, on the other hand, is a bit more limited, both in terms of the span of data that we're working with, as well as the input features. Feature-wise, we're restricted to just the things that KAISO forecasts, which isn't much. But we have demand and net demand forecasts on a day-ahead basis, as well as hour-ahead demand forecasts. But the key thing here is that because we're providing the model with both demand and net demand, it essentially, through the difference between those two, has access to a renewable forecast. Yeah, so the main thing that we noticed that shaped how we trained and tuned these classifiers has been by looking at if you look on the right side here, this is the distribution, at least in our data set, of the sizes of the curtailments. And you notice that most commonly curtailments are quite small, but you can tell, there's a decently heavy tail here, or there's at least something out here. And it turns out that there's enough of these larger curtailments, these higher impact curtailments, such that most of the total energy that we're dealing with here, most of the opportunity to use for something like a shifting application actually exists in these larger samples. So our idea, noticing that, was to try to encourage precisely identifying these higher energy samples in order to kind of both identify the best opportunities for shifting and also as a method for increasing precision by being able to ignore some of these smaller curtailment samples that are likely to be very close to whatever decision boundary you could draw. So, to kind of quantify this, we use a metric that we introduced and call energy recall, whereas normal sample recall, as you guys probably know, is just the true positive rate, or the percentage of positive samples that are classified as positive. For energy recall, we're instead concerned with what the percentage of the total curtailed energy content is in our true positive samples. So to kind of illustrate that really simply, if you have a data set like this that just has 2 positive samples, so non-zero curtailment in both, but we get the first one wrong, but we get the second one right. Normal sample recall would say we got one of the 2 samples right. We're at 50% recall. But energy recall would say we're at 99% because the sample that we got correct makes up 99% of the total energy here. And I guess one point of clarification, a lot of these are written as megawatts instead of megawatt hours. Yeah, that's just because KAISO is providing data in terms of the power rating within a 5-minute increment. So if you want to convert between power and energy, like on that histogram, just divide by 12. But anyway, the way that we actually use this energy recall sample in the tuning of the model is just to kind of create what's essentially like it's a modified version of the area under the precision recall curve metric, essentially. The only difference is we're using energy recall instead of normal sample recall. And we're also, because we're interested in this kind of high precision regime, we're only calculating that area for this kind of high levels of precision. So we use that to select hyperparameters for the model. And then the other thing that enters into this goal of precise identification of high curtailment samples is during training, we also weight the importance of the samples by the curtailment magnitude. So a couple of numerical results. Well, okay, I guess first, in these next slides, when I'm saying raw output, technically, I guess I mean the softmax of the raw output for the positive class. Some people call it that probability, but I'm not a huge fan of that term. And you guys probably know threshold. This is just the number at above which we classify it as positive in the binary sense. So looking at the results for the real-time classifier, the main takeaway is that through that tuning process, we've essentially accomplished what we wanted to, at least on this data. You see we have high precision of almost 98%, and then high energy recall of 95%, while only actually correctly classifying 70% of the positive samples. And the reason why that works is in the figure on the right here, you can see those false negative samples that we're missing tend to be smaller, small curtailment samples. And you can see that this effect remains true over a range of thresholds here. So you still have that gap between, you can crank up your threshold higher and still have a good energy recall in this case. And it's essentially the same story for the forecasting classifier. You have this gap between recall and energy recall here. The only real difference here is that you have kind of lower overall performance as compared to the real-time classifier. And that's likely just because we're more limited, at least what we've done so far. We're more limited in our input features as well as the time frame of the data. And I didn't mention it before, but the reason for the limitation of that, the time frame of the data is that day-ahead net demand forecasts were not available until August 17th, 2021. And I just want to, there's two case studies in the paper itself, one for the real-time classifier and one for highlighting what the forecasting classifier can do. But I just want to zoom in a bit on the forecasting case study that we did. And to illustrate how to use that classifier, how it could be used, we just put together a really basic data center load shifting problem. And yeah, I know there are a lot of people here who are very into modeling of this kind of thing. So this is a very, very basic data center load shifting setup. But essentially, we just take, we use the test set of the forecasting classifier, so a year's worth of data. And for every 24-hour period, we solve this optimization problem where we're essentially distributing the load across all the time steps subject to some kind of operational constraints. Operational constraints here that the total power has to be consistent, the same as it would be if you had flat load over the day, limits on flexibility at each time step, as well as ramping limits here. And we optimize the alignment. The goal here is to optimize the alignment of the data center load with curtailment, CI here. And we've got a couple different ways of measuring that. We try using the binary output of the classifier, which again is tuned to be quite conservative. It's aiming to kind of miss out on some of these smaller samples in service of being precise and identifying large curtailment samples. So to kind of check the effect of that, we also see what happens if we just optimize based on the raw classifier output. And then we also benchmark those against a perfect information case where we're actually giving, we're providing the actual curtailment amount. And the rationale for trying, one of the rationales for trying this raw classifier output idea is, obviously we're not doing regression here, and we haven't really tried to make this any kind of calibrated model exactly. But this is just showing there is a kind of a rough correlation between the output of the classifier and the magnitude of the curtailment, which sort of makes sense if you just consider like a more extreme case where net demand is super low, is likely to have more curtailment and be further away from the decision boundary of the classifier. All right, and of course these are all compared to, we used 100 megawatts, but it doesn't really matter, just a kind of a constant load base case, and that's how we generate results for this as well. Yeah, so in comparing this to these methods to the base case, we look at a couple of things. The first is just how much power was shifted overall, and the second is how much curtailed energy was saved, meaning how much additional would be curtailed energy was used as a result of shifting more power into some time steps. And the basic gist of the results is that both methods used both binary using the binary output or the raw output of the classifier both give you significantly more use of curtailed energy. So the classifier is able to inform scheduling on a 24-hour horizon. Of course, the numbers here are a function of how much flexibility you assume in your what the operational constraints of your data center are. So I wouldn't read too much into the numbers themselves. But the other key thing that we notice here is that like I said, the binary, the classifier is trained to be quite conservative, meaning it's only trying to identify large curtailment samples. So as a result, if we look at the percentage of the shifting that actually resulted in increased use of curtailed energy or would be curtailed energy, you can see using the binary output, you have much more certainty that the power that you shift or the energy that you shift will actually be used for or will actually come from curtailed energy. So gonna kind of wrap things up here. We've proposed two different real-time deployable solar curtailment classifiers, one for real-time and one for forecasting. And it seems as if they can reliably identify high curtailment samples with high precision, and that they may be useful for a few different applications. So I'll wrap things up there. Thank you.